What's up everyone? I'm Professor Jennifer Hill and this is my channel Divide and Conquer Math. This is both a YouTube channel and a website designed to help you learn math on your terms. So the whole idea behind these videos actually came from conversations with my students. So when I teach a lot of classes, a lot of times there's just not enough time in the schedule to do as much review as I would like for exams. And so I decided to make an entire video series that would kind of hit the needs of my students for any type of problem that they might want, and also kind of follows my philosophy of exams. So if you've never heard my philosophy of kind of how you should study for exams, I will drop a link right here, or you can look in the description and you can watch my video where I kind of give you some advice on, how to approach that. So this video is the second in the series. Like I said, it's on medium or average difficulty limits. And so the way that this is going to work, I don't teach you what you need to know for an exam. I instead give you lots of things to practice, because that is truly how you will study for an exam. It's practice, practice, practice. So you need the problem set, which you can get by just downloading it. It's in the description below. The problem set has really everything that you need to get prepared for a test as far as practice problems go. So there are problems, there's an answer key, there's also links to different videos. If you are doing a problem and you realize, oh, I totally forgot how to do this and I could use a refresher, I've got you covered, so you could just look in the whole problem set guide. Everything you need is there. Now, if you get a problem wrong and then you want to see how to actually do it, you can once again look in the description of this video and you will find time markers for every single problem. So basically, between that document and this video, we should have everything that you need to kind of conquer these types of problems. Now, I made this problem set for my students. If you are not one of my students, you might see some problems in there that are not going to be covered in your class, so modify the problem set to your needs. We're going to start where you will see me kind of working on my own stuff for about an hour, and I set that up just in case you have trouble getting started. You could consider studying next to me, and maybe that's a good way to help motivate yourself. And then after about an hour, I'll tell you time's up, and then I'll start going through the problem set. Now, of course, if you want to keep studying, you can always start the timer over, or you can just hit pause, whatever you want, but that's just there in case that's something that maybe helps motivate you. Okay guys, so let's get to it. Okay guys, it's been about an hour, so if you're not done, hit the pause button here. Otherwise, I'm going to jump into the problems. Okay, so starting with A here, so the thing that you'll notice is if you plug 5 in, you get 0 over 0, which tells you that you have to try something else. So the thing that you have to try here is you have to just factor the top. So the top will factor as x minus 5 times x minus 2, and then by doing that, you'll notice that I can cancel out, oops, that's 5, not 2. I can cancel out the x minus 5s. And so then that just leaves me with the limit of x minus 2, which is totally fine, and I can plug in 5 right into this. So this will give me 5 minus 2, which equals 3. So we're good to go. Okay, so if you missed this problem, what I would recommend is that you look in a calculus book for where the limit laws are introduced. This is usually like one of the first types of limit problems that you're given. So you can practice a couple more with this and maybe try some with trickier factoring. Okay, so for B here, very similar to the last problem. So notice if you plug in the -1, you're going to get 0 over 0. So that tells you then that you're going to have to think of something else. In this case, you're going to factor. And for this problem, you need to use the sum of cubes, which I have written out here. A lot of students forget it, but it's something that you actually really need to know for calculus. So if this is something that you find that you frequently forget, try to take a few minutes to actually force yourself to memorize it. Okay, so I'm going to go ahead and factor the top then using the sum of cubes. So this will be x plus 1 and then x squared minus x plus 1 over, and then the bottom will just be x plus 1 and then x minus 1. And now you can see from here that I'm just going to cancel out the x plus 1s. And so now I'm really good to go here. So I've got this, and now I won't have that 0 over 0. That's basically what we're looking for. So I can just go ahead and plug in -1. So I'm going to plug in -1 like so. And so this is going to give me 1 plus 1 plus 1 over -2. So this will end up being -3 over 2 for your answer. Okay, so this is what I would consider to be like a harder factoring type problem. And if you are looking to do more problems like this, I recommend that you look in a calculus book for kind of like your basic limits or limit laws, and they will probably have more problems that look like this, and just look for ones that have like the trickier factoring. So force yourself to do a handful of those. Okay. So for C here, so again, like the first thing you want to notice with this is that if you plug in the number here, you get 0 over 0. So because I get 0 over 0, that tells me that I have to think a little more creatively here. So in this case, this is a complex fraction. I will drop a link in the description next to this problem of just like if you totally forgot how complex fractions work, you can watch. I have like a whole video I made on it for another class, so you can check that out. So what I need to do here, or what I like to do, there's more than one way to do this, but my preference is to get rid of the fractions, because I just think it's the fastest way to approach this. So what I'm going to do is I'm going to multiply this by the LCD of these two fractions. The LCD of these two fractions would be 4x. And whatever I do to the top, I also have to do to the bottom. So I have to multiply the top and bottom by the same thing. So just to be nice and clear then about what we get. So I'm going to have 4x times 1 over 4 minus 4x times 1 over x. And then this will be 4x times x minus 4. So you can see now how I have this set up. And so basically what I'm going to do now is like looking in this cluster, so the 4's will cancel out. And then in this little cluster, the x's are going to drop out. So what I'm ultimately left with then is x minus 4 over 4x over x minus 4. And lo and behold, now this just happens to work out that these both cancel out. So I can cancel out now this and this to get the limit as x approaches 4 of 1 over 4x. And now I can just plug in the 4. So this will just be taking 4 times 4. So the limit in this case is 1 over 16. Okay, so if you struggled with this one, you can look in your calculus book for kind of just where limits are first introduced, so where the limit laws are first introduced. Wherever that section is in your book, you'll probably find a few questions that look like this, so you can flip to that area and then try other questions that look similar to this. Okay, so for D here, so notice if I plug in 0, I get 0 over 0. So that's like always the first thing that you want to check, and that's the reason why we have to try using kind of other techniques. So because I have a square root here, I want to try using the conjugate, which the conjugate is found by just taking that square root and then flipping the sign kind of in between this binomial. So this is really a two-term expression here. So we can just rewrite it like this. And so this is what I can multiply out. All right, so if I multiply the top part together, I get x plus 9, really minus 9. That's what everything simplifies to. And maybe just as like a really quick aside, so the way that this would factor, I'd get x plus 9 plus 3 times the square root of x plus 9 minus 3 times the square root of x plus 9 minus 9. So these square roots drop out, so I'm just left with this. So just showing you kind of how I got to that. Okay, so I've got that over x times the square root of x plus 9 plus 3. All right, now pro tip here. I recommend not actually factoring out the bottom, because a lot of times what ends up happening with these problems is just it'll work out that something down here will probably drop out. And then if it doesn't drop out, then you can factor it out. So like just hold on a second before you do this. Okay, so now I get x over x times the square root of x plus 9. Let's see, make that not such a big square root. X plus 9 plus 3. So you can see here then that my x's drop out. So I'm just left with the limit as x approaches 0 of 1 over the square root of x plus 9 plus 3. So now I can go ahead and plug in the 0. So I get 1 over the square root of 9 plus 3. So this comes out to 3 plus 3 is just 6. Okay, so once again, if you missed this one and you want to practice more, look in your book for where the limit laws are first being introduced, and sometimes one-sided limits will also have problems like this, but you should be able to find problems that look like this that you can practice more of if you got this one wrong. Okay, so moving on to E here. So in this case, so notice if I plug in 0 over 0, or sorry, if I plug in 0, I get 0 over 0. So that tells me that I'm going to have to think creatively here. Whenever you get 0 over 0, you have to think creatively. And then notice I can't simplify this any farther. So you cannot cancel out the x's, right? That's not a thing because this is sine of 5x, so this is kind of its own function. So what this tells me then is I have to think a little more creatively and think about what other things do I know. There's really no like trig simplification I could make to this. So what I'm going to want to use here is that limit as x approaches 0 of sine of x over x. This is kind of the theorem that I want to use here. So I've talked about at length in another video, which I'll post a link to it in the description next to this problem. So really the thing about using this particular theorem is you can have like really the key form that you want here. This and this have to be the same, and if those are the same, then this equals 1. So this is like a whole proof behind this. I've done this a lot of times if you want to reference some other problems like this. So basically the problem right now that I have is that this is 5, this is not 5, right? So I have 5x and then just x. So I just have to manipulate this so that the top and bottom at least kind of have the same thing. So to do that, what I'm going to do is I'm going to multiply the top and the bottom by 5 like this. So I really don't need the top 5 here. Like I really just wanted this bottom 5, but whatever I do the bottom, I have to do the top. So here's how I want to think about this now. I'm going to factor out this 5 out in front. So I'm going to put this in gold so that you know what 5 I'm talking about. And then I've got sine of 5x over 5x. So this was this bottom 5. So now I really have this in the format that I want. So this whole thing, this equals 1. So this whole thing now will be 5 times 1, so this equals 5. So that's really the only way that you can get to this particular answer. So it really does matter how you show your work. If you show your work in an incorrect way, then you would very likely get it wrong probably in most classes. So you know, if you're looking to do more problems like this, so this is a little bit dependent now on the calc book and what your teacher thinks is important. So not all calc classes use this. But if this trick is something that you are using in your class, which we do in mine, you're going to want to look for the section where this was introduced. So you might have to dig a little bit. In my book, it's introduced in one-sided limits, but sometimes it can just be introduced as like a trig law, or like there's a lot of different ways that this can kind of pop up. So you'll have to just look where this is introduced. In whatever section this is introduced, excuse me, then you can just look in that section for more problems that look like that. I've also done a ton of problems like this, so I'll go ahead and drop a link to some of my example videos if you want to just watch more examples. Okay, so moving on to F here. So for this one, it's usually best practice if we rewrite like tangent or cotangent in its, actual, like write the whole thing out. So instead of writing this as cotangent, I'm going to write this as cosine of 3x over sine of 3x. And so the thing to notice now is if I plug in 0, I'm going to get 0 over 0. And then the second thing to notice is that there's really no other simplification I can make here that would be meaningful. And then the next thing to notice is that I have x and sine of 3x. So I have actually, I'm still using this little property here. So let's see, maybe I'll write this in terms of theta. So I've got this theta approaches 0 of sine of k theta over k theta equals 1. So just FYI, so this is the theorem, but it's actually equivalent to say, so I can also do k theta over sine of k theta. These are equivalent to one another. So the fact that I have this x on top and the sine of 3x down here, that's like almost in this form if I just manipulate it a little bit. So that's usually the hint that you're looking for, is that you can't simplify any farther. You're getting 0 over 0, so you're probably going to have to use this little gem of a theorem here. So what I want to do is I just want to kind of rearrange all of this, because basically I'm trying to line this up so that I can use this. So I'm going to, okay, so here's x approaches 0. I'm going to put this x over the sine of 3x. So I'm kind of breaking things up here. So this 4, I'm going to move with this cosine of 3x. So I can just kind of move stuff around like this since it's all being multiplied anyways. Okay, so I've kind of broken stuff up. And so now what I want to focus on is being able to use this theorem right here. At the moment I can't, because this is x and this is 3x. So very similar to what I did in the last problem. So I'm going to multiply the top and bottom by 3. Okay, now I really only wanted this 3, but whatever I do to the top, I have to do the bottom. I have to keep it equal. So what I'm going to do here actually is, just like I did in the last problem, I'm going to take this 3 and just factor it out so that it's not distracting me. So I'm going to write that 3 in gold. So this is 1/3, so because it was in the denominator, right? And then I've got the limit as x approaches 0 of 3x over sine of 3x, and then times 4 cosine of 3x. All right, so now we're in business. So this guy right here is going to be really an application of this theorem. So this is going to go to 1. And then this, if I plug in 0, cosine of 0 is just 1. So this is going to be really 4 times 1. So at the end of the day, the way that this looks, this is, so don't forget about this 1/3 over here. So this is 1/3 times 1 times 4 times 1. So this just equals 4 over 3. Okay, so if you are looking to practice this more, so I talked about this in the last problem too, but not all calc books stress this limit. In my book we do, and in my class we do. So if this is something that you've used in your class, then you basically want to look for the section that introduced this theorem. Wherever that was introduced, that section of problems will have more problems like this, and then you can practice. I'd say like practice a good handful if you struggle with these, because these problems are kind of difficult. Okay, so moving on to G here. So now we've got a one-sided limit, and so we've got this absolute value. So there's a couple different ways that you can kind of handle this. If you're super nervous, you can always just try to make a table. So I've got my x's, And then let's say that I plug this in. So what I could do is I could choose a couple of x's really close to 3, but just above 3. So like 3.01, 3.001, and then 3.0001. I could do this and plug them just straight into this to see what I get. So if I do that, these are the values that I will get. So I just went ahead and plugged them in and worked it out. So this is like one way I can double check, and I can kind of see that the closer I get to 3, right, the closer I get to 4. But I'll warn you. So a lot of times, not all calc teachers are going to let you use the table. A lot of times you have to prove things algebraically, which you can totally do with this, by the way. So the thing just to know about this is it might be helpful to actually graph this out and see it. So let's actually just take a really quick look at the graph. So this is desmos.com, totally free graphing software, one of my favorite places on the internet, honestly. So I went ahead and just graphed this here. And so remember, we're at 3 on the right. So here's where, like, this is just where I'm really close to 3. So here, like, here's what's happening with this function. It basically breaks off into 2 pieces at 3. So if you have the graph in front of you, you can see really clearly, like from the table now. So here was the table that I did. So that at the table, we can see that we're getting really close to 4. And then from the graph, I can see I'm really close to 4. So now the thing to think about here, and just to kind of recognize with this, is how the absolute value works. So absolute value, so let's think about this for a moment. So absolute value, if I just think about, let's pretend I have just some different function here for a moment. So if I think about how this works, so absolute value looks like this, just in general. And so basically, like, absolute value has this v. So like this side, when I'm on this side, this is like the positive side. So this side of the graph right here, this would be just the graph x. And then this side here, this is the graph negative x. And so basically what ends up happening is that you get to this zeroing point, and then it kind of splits off. So the thing you can kind of think about this and apply it to this problem, in that you're going to have like a positive arm and a negative arm of this. And so here, so you can see if I plug in 3, that's going to be kind of the zeroing point for our absolute value function. So that would be kind of the corner. So if I'm just to the right of 3, that's going to put me on the positive arm. So like this behavior here is kind of helping us to understand the behavior here. Now, of course, it gets a little all complicated because I've got this x plus 1 and then this other x minus 3. But you still have this behavior of x minus 3, the absolute value of x minus 3, kind of influencing the whole function. So because of this, I can also really say, like, I'm on the positive arm of x minus 3, so I can rewrite this function. So let me clear some space. And okay, so I just want to rewrite this now. So instead of writing this as the absolute value of x minus 3, since I know I'm on the 3 to the right, I can actually just say with confidence, this would be this function, just x minus 3. Okay, so the reason I want to do that is because now I can actually cancel out these x minus 3's. So now I'm just left with the limit as x approaches 3 on the right of x plus 1. And there's no issue with this anymore. Like, I can just plug in 3 into this. So I'll just get 3 plus 1, which is 4. And that's exactly what we saw on the table and on the graph, right? But now we've proved this algebraically. So this is a really strong way to do this. And so just to round out this topic, if I were on the left side, so I think the really common question is then what happens if you're on the left? So the way that you would rewrite this particular limit, so then you would be on the negative side of this function. So what I mean is I would put a negative here. So I'd have x plus 1, x minus 3, and then x minus 3. So that's how I could kind of represent this whole function. I would put a negative here. So here I had no negative, but since if I were on the left side of this, then I would put a negative to represent the side of the function that I'm on. So I have other videos where I kind of explain this more. So if you want to watch those, I'll drop some links to those videos in the description of this one. Okay, and so what if you want to practice more like this? This is a really common question when you are studying one-sided limits. So you can look in your book and you'll probably find some problems that look very similar to this. And then, like I said, I'll also drop some links to some video examples, and you can try those as well. Okay, so H and G are like almost the same problems. So if you missed this one, you might want to watch my explanation on G as well. So basically the idea behind this is that now I'm getting to, so at -1, I'm going to have this 0 over 0 problem. But I know that I'm on the left side of -1. And so I talked about this at length in G. So I am going to just refer you back to the other problem to see the complete explanation. But basically I'm on the negative side of this function here. So what I can do is I can rewrite this like this. So this will be rewritten like this. And so if you want to see why does that work like this, just watch the explanation in the last problem. Okay, so by rewriting this problem like this, what this allows me to do is then actually cancel out the x plus 1s. So then I've got the limit as x approaches -1 on the left of x plus 4 over -1. And now I can just plug in -1. So I get -1 plus 4, all of that divided by, oops, sorry, not -3, divided by -1. That's the final answer. So then I get 3 over -1, so then this equals -3. So this is a really common problem for one-sided limits. So if you're looking to practice this more because you got it wrong, just look in your book in the one-sided limits and you'll probably find other problems that look very similar to this. Okay, so moving on to I here. So in this particular problem, so you might want to know what the graph of just 1 over x looks like. So if you don't know the graph of 1 over x, this is one of the graphs that you really need to know for calculus, because just having this picture in your mind will help you with problems like this. So notice with this problem, if I just try to plug 0 in, I get 1 over 0, that's a problem. So I can't simplify this any farther. So what that tells me is this is probably going to go to either plus or minus infinity. So now I just have to figure that out. Which one does it go to? Now, like the tried and true method of really showing that you know where it goes is by just choosing a few values that are just to the right of 0. So just to the right of 0, so I could do like 0.1, 0.01, 0.001. So I plugged in those values, and here's what I got out if I just plug those in. So the thing to notice with this is the behavior. So these are all positive. So these are all positive, but they're also getting larger, right? So the smaller my number gets, the bigger this is getting. So what this tells me is that the closer I get to 0, the more this is just going to get huge. So this is just going to go to positive infinity. So I do recommend that when you take a calculus test that you do try to show this type of reasoning. I think that it actually, like, if you do enough of these problems, you can probably just look at this and figure out where it's going to go. But you do want to have some way just to kind of show your reasoning. And so having the table is just a good way to kind of prove to your teacher that you've really got it. Okay, so starting here now with J, so very similar to the last one that I just did. So with this one, notice if I try to plug in 0, I get 1 over 0, so that's a problem. So what I'm going to have to do here, though, is this problem's a bit harder than the last one because this just goes to 0. So to figure out where this is going to go, I actually need to break this particular limit up into 2 pieces. So I need to evaluate the limit of 0 on the right, and then the limit of 0 on the left. So this is what I've got to do. So what I can do here is I can make a table for each of these just to kind of analyze the behavior. And so notice that on this side, so I'm just on the right of 0. These are points that are just to the right of 0. And then I want to be just to the left of 0 with these other points. 0, 1, and then negative 0.001. Okay, so if I plug these in, so here's what I'll get. So just kind of doing a quick analysis with my calculator. So I can see here that the closer I get to 0, the larger my number gets on the right side. And then on the left side, the closer I get to 0, the more negative but large my number gets. So using this analysis here, I can see that on the right side, this function is going to positive infinity, but on the left side, this function is going to negative infinity. So what that means then is since this limit is going to 2 different values on the left and on the right, this limit does not exist. But just FYI, like when you take a test, it's not enough. Like sometimes what I'll see is a student will just write does not exist. Don't do that. Okay, like on a test, the whole point is that you're trying to prove that you know what you're doing here. And so I have students that will write do not exist for like every limit problem. So if you just write that, like I've had that happen, believe it or not, every single problem does not exist. Or I've had a student just say, I don't know how to evaluate this, so I'm just going to say it does not exist. So if you just write does not exist, that doesn't show that you know why it does not exist. So if you know something definitely does not exist, you need to kind of put forth the whole argument to show why that happens, like some sort of explanation. I think in a lot of classes, it's not going to be enough just to say it does not exist. Okay, and so if you want to do more problems like this, you can look for problems that are on infinite limits or limits that equal infinity. So this is usually like something that's discussed in a separate section. I've seen books. I'm kind of a nerd, so I have looked in lots and lots and lots of calculus books. And so some books will like have a whole section on limits with infinity. So this will be like a section in those books, and then other books will have like a whole section just dedicated to problems that look like this. So you have to figure out what your book does, but you know, check that out, and you should be able to find plenty of other practice problems on this. Okay, so K here. So this is another one. This is similar to the last two that I've done. So if you plug in 3, you're going to get 1 over 0. That's a problem. So there's no other way to simplify this. So the only way that you can really do this then is you're just going to have to analyze what happens as you get close to 3. But for this type of problem, you want to analyze this on the left and on the right. So if I do the limit as x approaches 3 on the right, okay, so here's this first one. And then I've got the limit as x approaches 3 on the left. Okay, so there's like my breakdown. So what I want to do now is I basically just want to plug in a few values to kind of analyze this. I'm analyzing the behavior. So just to the right of 3, that would mean just above 3. So that's going to be 3.1, 3.01, and 3.001. So basically I'm just trying to get closer and closer to 3. And then just below 3, so to the left of 3, that would be like 2.9, 2.99, and then 2.999. So there's kind of my breakdown. Okay, so now if I actually evaluate this, so here's what's happening like numerically with these limits. So the closer I get to 3 on either side, the limit gets bigger and bigger and more positive. So these are both going to infinity in this case. So infinity and infinity. So this particular limit will equal infinity. Okay, so just a word of caution again. It's not enough to just write infinity. I have had students who just take like a wild guess. You do want to show your reasoning as to why this works. And so it's really just as simple as just kind of, you can make this like numerical argument. And you know, it also kind of makes sense, I think, because it doesn't matter, you know, if you're on the left or right of 3, since this result here is getting squared, you can kind of see that it's going to stay positive. But you want to make sure that you have something to kind of present your reasoning on your test, if that makes sense. So if you want to practice more problems like this, just look in your book for a section on infinite limits or limits at infinity or limits involving infinity. So I talked about this in the last problem too, but sometimes calc books will break problems like this out separately, and then other times calc books will just have like all the limits that have anything to do with infinity and put them all together. But either way, you should be able to kind of find more problems that look like this. These are pretty standard limit problems. Okay, so for this problem, so now we've got x is going to infinity, and this is really just like a polynomial over a polynomial, so this is a rational expression. The fact that this goes to the fourth, this is really just noise here, so I'm really just curious as to what's going on with the exponents here. And so the thing to notice with this problem is, where is the largest exponent? The larger exponent is in the bottom, so what that means is that this term is really going to drown everything else out. And so when that happens, when the largest term is in the bottom, that really just means that the whole thing is going to go to infinity. Or sorry, to 0, 0, 0, 0. Okay, so let's just see how to analyze this. So one way you can kind of prove that to yourself is you can divide everything by the largest power of x. So if I do that, So I'm just going to go ahead and set this up and divide everything by x to the 6. So I'm going to go ahead and divide this by the 6, and I'm going to divide this by the 6, and this, and this, and then all of this, x to the 6 over x to the 6, minus 2x to the 4th over x to the 6, plus 5x squared over x to the 6. Okay, so all of that stuff. Okay, so I've got all of this now still to the 4th. Again, this is just really noise. So I can simplify all of this. So let's see, I've got the limit as x approaches infinity of 1 over x squared plus 3 over x to the 3rd minus 2 over x to the 5th plus 1 over x to the 6th. All of this over 1 minus 2 over x squared plus 5 over x to the 4th. Okay, so now looking at all of this, so like the key thing to know here is that really these limits, 1 over x squared, as x goes to infinity, like this is going to go to 0, this is going to go to 0, like all of these are going to go to 0. This is also going to go to 0. So basically I'm just left with, when I take this limit, 0 over 1, which equals 0. So that would be the limit, that would be the value of your limit in this case. And it's really because we have this like x to the 6th drowning out all the other terms. Oh, just one other thing with this one. So if you are looking to do more problems like this, just look for problems that work with x going to infinity. This is a really standard type of problem, so you should be able to find more of these in any calc book. Okay, so for this one, so very similar to actually what I did in the last one. So this is a limit going to negative infinity, and really, like, even though you have square roots and rational exponents, you, like, at the end of the day, like, this is really just kind of its own rational expression, and we just need to really investigate the exponents. So the first thing that I want to do here is I want to rewrite this to x to the 1/2, and then so this x to the 1/3. Okay, so first things first is I just rewrite all the exponents, and then from here what I want to do is I want to change these exponents so that they all have the same denominator. So basically, like all of these x's, I want them to have the same denominator. You'll see why in a second. So if I rewrite all of these with this same denominator, so the denominator will be 6. So this will be 3 over 6. This will now be x to the 2 over 6. And then this will be x to the, let's see, 12 over 6. Oops, 12 over 6, not 16. 12 over 6, and then x to the 6 over 6, and then just 1. That 1 doesn't have any x's, so we can't do anything to it. Okay, so the thing about this one is that you just want to notice now, where is the dominating term? So where is the term of highest degree? And so once again, this is in the denominator. So if I wanted to, I could really divide everything by that term of highest degree, just like I did in the last problem. So let's see. So why don't I make myself some space? And now let me set this up. So I'll just show the division. Okay, so I've set this up, so now I can really just kind of use exponent rules here to simplify all of this. So let me make some space again. And now I'll simplify. Okay, so this was kind of a lot of extra work, but I wanted to be really thorough just to kind of show you like why this works. So like you don't have to technically convert all these exponents. Like if you can do this without doing like the conversion, that's okay. But I think a lot of people are really visual, so having like all of this detail kind of in front of you can be really helpful. And so basically, now what I have here is, you know, this is 5 over x as x is going to infinity. So this is going to go to 0. This is going to go to 0. These are all going to go to 0. So this is a whole lot of work just to get 0 over 1, which equals 0. But that's like the approach you can take. So hopefully that's helpful. Okay, so if you're looking to practice more problems like this, you can really just look for the section where, you know, limits as x is going to infinity, where that's introduced. So different books do it in different ways. Sometimes it's its own separate section, and sometimes there's like a section that will just have like all limits that have anything to do with infinity. But you can totally find more problems that look like this, and so you can just search in your book to find those. Okay, so moving on to n here. So this one is going to be very important to pay attention now to your dominating term. So by dominating term, I mean where is the term of highest degree? So it would be x to the fourth. So what this really is telling you is that in this case, you have the highest term on top, so it's really getting drowned out by, like, everything's getting drowned out by this. So as x goes to infinity, this whole thing's really going to end up going to infinity. But here's the plot twist with this one. So the problem is that you have x is going to negative infinity. So how can you figure out if this goes to positive or negative infinity? So what you can do here is there's actually a really simple trick that you can use. So you can divide by the term of highest degree in the denominator. So let me show you why you'd want to do that. So I'm going to divide the top and bottom here. And so what I'm going to get here is, so this is going to give me x plus 2 over x to the third. And then this will be 1 plus 1 over x to the third. So I just went ahead and divided each of these by x to the third. Okay, so the reason that I'm doing this is this just helps me to kind of narrow in on what's actually happening with this. So in this case, like this and this, these are both just going to 0, right? So what I'm left with is this x over 1. Like this is kind of like the essence of the problem. So if x is going to negative infinity, that means that this is just going to end up going to negative infinity. So I get kind of this idea of almost negative infinity over 1, but just FYI, this would be bad. Don't write negative infinity over 1. Don't do it. Do not do calculations as if you can plug in infinity. That is usually a big no-no with a lot of math teachers, so I wouldn't do it. So instead, you can just kind of go to the final answer, which would just be negative infinity. So infinity is kind of this concept, right? So we can't do calculations with it technically, even though I get why your brain wants to do that, but you have to be really careful when you do that. So if you're looking for more problems like this, just look for more problems as x goes to infinity, and you should be able to find a lot more like this. Okay, so moving on to O here. So for this one, so what happens then as x goes to infinity in this case? Well, this is e, so this is just a positive number, right? And it's a positive number going to a positive exponent. Okay, well in this case then this is just going to get bigger and bigger and bigger, so this is just going to go to infinity. That's really it. So nothing really to this here. Like, since this is something positive just being brought to something more positive, it's all going to stay positive and it's just going to grow infinitely. But let's contrast that to p. Okay, so I can actually rewrite this in a way that might help me view this a little differently. So I could change this as x goes to infinity, but take this negative and basically transfer it into the x. So this is the same thing, right? In essence, this is the same thing. But the reason why this is helpful is if I think about this, I could rewrite this expression with this negative exponent. I could rewrite this as 1 over e to the x. And so by rewriting this, oops, sorry, this should not have an equal sign here. I could rewrite this as 1 over e to the x. And so the reason that this is helpful is then I can see that really I've got this fraction with the denominator getting bigger and bigger. And so whenever that happens, that means that the whole thing's actually going to go to 0. So that would be the answer in this case. Okay, so moving on to Q here. So this problem, I think, just throws people off because it's got a ton of trig in it. But at the end of the day, there's like nothing wrong with just plugging in the number and seeing if it will work. I mean, because you will either encounter like a 0 over 0, or you will encounter something that does not exist, and then you've got to think more analytically about it, or it's going to work. So in this case, let's just do it, okay? So I'm going to just plug in pi like this. Okay, so if I analyze this, so this sine of pi is just 0, so this whole part right here will just simplify to just pi. So I get inverse sine cosine of pi, and then the cosine of pi is -1, and then I've just got to think of what is inverse sine of -1. So you might want to bust out your unit circle to help remember this. And by the way, that's like a really key thing you've got to be able to do really on like any calculus test. If you don't have the unit circle memorized and problems like this give you issues, you want to just take some time to memorize the unit circle. Like, force yourself to do it like 5 times a day, every day, until you have it down, because sometimes that's really the best thing you can do for yourself on a test is draw out the unit circle and just get it done. Okay, so the inverse sine of this is actually just going to equal pi over, or negative pi over 2 is what I meant. Okay, so, all right, so that would be the answer in this case, so negative pi over 2. And this has to do, it's negative pi over 2 because that has to do with the range of the actual functions. That's another thing you can look up. Okay, so moving on to this next one. So everything's actually going to be continuous here at 0. So I can actually just kind of plug this in and use this as a composition of continuous functions. So here's basically what I mean. Like, you can see if this works, and then if it doesn't work, then you have to think of something else. But if I just start by plugging in 0, so sine of 0 is just 0, so then this will be cosine of 0, right? And then the cosine of 0 is just 1. So then I've really got cotangent of just pi over 2. So that's going to equal, well, if you're not sure, you can always just plug it in. So I've got cosine of pi over 2 over sine of pi over 2. So that's 0 over 1. So that just equals 0. So that would be the answer in this case. So this is usually something that's brought up with like continuity or like limits of continuous functions. So a lot of times you can find limit problems in your section on continuity. You might find a couple like this. Otherwise, you can look in your book for limits of compositions of continuous functions and find more problems like this. So that's what you can study if you want to try that some more. Okay, so moving on to 2 here. So these problems, I actually think, so I've got these 4 problems here, so I'm just kind of bunching this section together. So I've got this piecewise function, and to be perfectly honest, I think that it's best if you know what the piecewise function looks like. So first things first, I'm going to just draw out this piecewise function, and then it makes evaluating the rest of this super simple. So if you don't know how piecewise functions work, I actually have a review of this, and I have, I think I have a whole video on this, how to do this as well. So I've got you covered if you need a refresher on this. So I'll drop a link to that next to this set of problems in the video description. Okay, so let's just get to it then. So the limit as x approaches -1 on the right. Okay, so -1 on the right, here's -1. And then on the right side, so the right would be over here. So this would be the more positive side. So I want to be on this part of the function, and I can see that as I get close to -1, this is going to equal 0. So this equals 0. And then what about the limit as x approaches 0? So here's 0 right here. And really it's approaching the same thing from the left and the right, so there's nothing special about this. So in this case, this would just equal 1. So this equals 1. Okay, so moving on to C here. So now I need to look at the limit on the left and the right of 3. So if I'm on the left of 3, so that's the more negative side. So here's 3. Here's the left or the more negative side. I have a whole video where I break that down if you're confused on how to figure that out. So if I follow this along, so let's see, if I follow this along, looks like I'm going to, yeah, 4. So this is going to 4. And then if I'm on the right side, so now I would be on this function here, and this is just the constant function of -2. So that would be the limit in this case. Okay, so moving on to the very last problem here. My God, I have been doing so many problems in this video. This took a really long time to make. Okay, so suppose you know that f of x is such that it is between these two functions for all x. Find the limit as x approaches 0 of f of x and state what theorems you used. Okay, so this problem is literally screaming for the sandwich or the squeeze theorem. So that is really what this is getting at. So what I need to do here is I need to take the limit of these two functions as I approach 0. So let me get some space. Okay, so what the sandwich theorem says is to actually just evaluate these two functions at that limit, so the limit as x approaches 0. So what I've done here is I've broken this out. So the limit of this function as x approaches 0, this is just going to equal 3. And then the limit of this function as x approaches 0, this will end up being 3 times 1, so that equals 3. So since both of these limits are 3, then by the sandwich or squeeze theorem, this limit is also going to equal 3. And you can look for problems on either the sandwich or squeeze theorem. Oops, I didn't write theorem right. Sorry, it's been a long video here. Okay, so you can look for problems like this look for the section that discusses this theorem, and then you'll probably find a few problems related to this. All right, and so that covers this video. So if you are looking for more practice, consider checking out the next video, which is just more difficult problems. I also have another video of like mixed levels of examples. Otherwise, thanks for watching, guys. If you leave me a like or a comment about what you thought about this, it would be really great. I'll catch you next time.